Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this section I'm going to continue my discussion on the planetary motion in astronomical units, and we continue our adoption of more convenient form of representing the planetary motion than the previous forms that we have seen. So we are talking about Kepler's motion in another form, Kepler's motion in another form, and we see that let us now rewrite our ellipsoidal motion, motion along the ellipse in another form. So typically our ellipse, I'm just drawing half of the ellipse of the orbit, and if we were to look at the corresponding circle for this ellipse, our circle is as follows, where the diameter of the circle is the major axis of the ellipse. So now earlier, let us say our F was the focus and our R was the distance of the ellipsoidal ellipse trajectory from the focus. We see that R was making an angle theta, and now on the circle, if we go to the circle and look at the distance from the center, right? So corresponding distance from the center, we will now see that this new angle is psi, right? So there is a relation between psi and theta. So our point of the planetary motion point is P, where the planet is at any given point of time, and let me call this C, and F is the focus, and let me call this point corresponding to P on the x-axis as N, and now we can see that my Cn is nothing but Cf plus Fn, right? So Cn is Cf plus Fn, and I can start to plug in all these values. My Cn is A cos psi, and I'm just using these formulas here, and my CF is nothing but A times E, so that is my distance of the focus from the origin, and Fn is R cos theta, right? So all in all, I'm trying to rewrite the equation of the ellipse not in form of theta but in the form of the angle psi from the center, right? So that is what we are trying to achieve. So now again we are going to use our path equation. Remember, our path equation, the ellipse equation is 1 over R is A by B square 1 plus E cos theta. So that was my equation of the ellipse, and E was equal to 1 minus B square by A square. And from here, what have we got? We find that what else have we got? We have this equation, we have this eccentricity, and we want to plug everything into this equation that we have. I think we also want to find what is R. So R, any given point of time, T, the time taken by the planet on moving along the ellipse, T is 1 over L integral 0 to theta R square d theta, right? So are we using this? I think we will keep it for the time being. We may not use this at this point. I think what we have is using, well, I think for ellipse we can use the path equation. So we use the path equation. The path equation, we find that, so we find the following, that we now have, after using the path equation and all these equation of the ellipse as well as the eccentricity and plugging it into this, this, let me call this as star. So path equation plus star, we find that our new equation is cos 1 minus e cos psi times 1 plus e cos theta is b square by a square, right? So let me call this as double star. Okay, so then now let us come back to this equation that we were looking at, the equation relating the time and the area of the sector, and we see that t is integral 0 to theta r square d theta, and of course r we can use from the equation of an ellipse, and from here we will see that this is also equal to, well, 1 over L. This is also equal to b4 by a square L integral 0 to theta d theta 1 plus e cos theta whole square, right? And this comes out to be after, well, we cannot still integrate. This is not going to be an easy integration because this factor is sitting in the denominator. So I'm going to change it into the psi equation. So this is b4 by a square L integral 0 to psi, and now d theta can be written as d theta d psi times d psi. So that is my d theta, right? Now d theta d psi, I can differentiate, well, I can differentiate this star. So differentiate double star implicitly with respect to psi, and I'm going to get the relation between for d theta d psi, and that is what I will plug it inside this integral to see that my new integral comes out to be t is ab by L integral 0 to psi 1 minus e cos psi times d psi. And this is an easy integral, and we see that this is ab by L times psi minus e sine psi, right? And so that is my equation which relates the time to the angle subtended at the center, right? So typically this is also the equation of the path of the ellipse, but now the equation is in the form of the angle and the time, right? So what have we got here? So from here, well, I can also relate this time to the period of the ellipse, right? So using L formula and the period formula, I see that using L formula and the period formula, I see that t is equal to tau by 2 pi times psi minus e sine psi. Okay, so t is equal to tau by 2 pi psi minus e sine psi, and tau being the period. Okay, so I have written my time of traverse in the form of the period, and this is my Kepler's equation for time as a function of position. So let me call this as 3 prime. This is my Kepler's equation for time as a function of position. Time as a function of position, or inversely I can talk about position as a function of time. Okay, position as a function of time. To calculate to calculate psi, and that is how we invert to find psi. Okay, and from here we can find position as a function of psi, and then we can use our, well, have I start, well, and we can use this equation double star. We can use double star to find that my position psi r is a times 1 minus e cos psi. Double star, and of course the equation of the ellipse to find that r is this quantity, right? So that is what we have. Okay, so then let us look at Kepler's equation. Let us look at an example of the application of this equation. Okay, so Kepler's equation to find time. So what have we got? So this is an example where we want to find the time of the motion of the body. So the body moves in an inverse square attractive field and traverses an ellipse with eccentricity e and period tau. Okay, so we need to find the time taken by the body to travel half the orbit nearer to the center of force, right? Okay, so we need to find, remember, the motion of the ellipse, the motion of the body in an ellipse is such that we need to find the time it takes to travel along half the ellipse, right? So we need to find, so the solution asks us to find t, the time of travel, for our angle psi such that psi is between minus pi by 2 to plus pi by 2, right? So psi was the corresponding angle that the center subtends on the circle with semi-major axis as the radius, right? So psi. Okay, so we are going to find this time. So time t is t of pi by 2. Our t of pi by 2 means pi by 2 plugged in our t equation, minus t of minus pi by 2, and this is going to be tau by 2, 1 by 2 minus e by pi, right? And we see that t over tau comes out to be 1 by 2 minus e over pi, and this is roughly equal to 0.18, and this is the roughly 18% of the total time, 18% of the period. So this is a very curious result, very strange result, that the time taken to travel half the distance on the ellipse is roughly 18% of the total period time, of the total period. If had it been a circle, we expected that E would have been 0. So for circle, E would have been 0 and the time taken would have been exactly 50% for half the travel. For an ellipse, it is 18%. So the results are non-trivial here, right? So we just cannot assume that half the distance means half the time, especially when the orbits are elliptical. Okay, so now I'm going to talk about a very popular problem of the transfer of orbits. Remember, we have so many. India is sending so many satellites in the space nowadays. ISRO is doing so many experiments. The question that arises in for ISRO is how to place a satellite from the Earth to, let's say, Mars. So Mars was the latest objective of ISRO. So how was this achieved? So I'm going to talk about this problem using this problem of planetary motion, or the so-called Hoffman's transfer of orbits. So this problem has is related to the Hoffman's transfer of orbits. Okay, so what we have got is Hoffman's transfer of orbits. Okay, so the idea is that, look, we have a planet, let's say Earth, right? And what we have got is, let me draw a slightly a better diagram so that it becomes easier, right? So here is Earth, and let us say here is our Mars, and ISRO wants to send a satellite from Earth to Mars, right? And what we have is that we want to transfer the satellite in such a way that the fuel consumption is minimum, in the minimum energy, minimum cost, right? And the way we want to do it is that there are certain constraints that is put on the satellite. Now, before we discuss those constraints, let us first discuss the assumptions in order to solve this problem of transfer of satellites from one orbit, one planet to other. So the assumptions in this problem is, so the problem statement is, first the problem statement is that we want to transfer a spacecraft or satellite from one planet to another, with least amount of fuel, right? So we want to transfer a spacecraft or satellite from one planet to another with least amount of fuel, right? And the assumptions are, we are trying to simplify our problem. It's already a very complicated problem here. The assumptions are that the planets are moving in circular orbits. Well, we just now said few minutes back that the planetary motion is in elliptical orbits. We are just negating our statement here. So we can just say that the planets are moving in nearly circular orbits. So the planets are moving in, well, let me put this in bracket, nearly circular orbits. Okay. And then the second assumption is the satellite is initially removed. The satellite is initially removed from the gravity. Let me call this this object A, and, well, let us keep it as E and M. So the satellite is initially removed from the gravity of Earth, E, but is close to A, right? So it is there right at the surface of the Earth when it is being removed, right? And orbiting, the Earth is orbiting the Sun as well. So, and orbiting the Sun in the same orbit as E, right? So here is our Sun at the very center, and the Earth is orbiting the Sun, and we are saying the satellite is initially removed from the gravity of the Earth, but it is close to Earth, right? The distance between the satellite and the Earth is negligibly small, right? It's just of the order of few kilometers. And it turns out that the satellite is also orbiting the sun along with the earth initially. Then the third assumption is that the firing time of satellite is negligible. The firing time of satellite is negligible, right? So the satellite, which means that the satellite receives an impulse before takeoff and landing, receives an impulse before takeoff and landing. Okay, so the satellite receives an impulse, which means the firing time is 0. Okay, so then with all these assumptions, we need to find out what is the net impulse. So if my takeoff and landing impulse changes the velocity, my takeoff and landing impulse changes the velocity by delta VA and delta VB, then my total impulse is delta VA plus delta VB, right? My total impulse is delta VA plus delta VB, and each impulse consumes fuel. So we want to minimize the fuel, we want to minimize the quantity capital Q, which is the total impulse, right? And this must be minimized. So I want to minimize my total impulse, because that is consuming my fuel, right? And so that brings us to our optimal orbits, or the so-called Hoffman's orbit. So the optimal orbit is the Hoffman's orbit. Right? Hoffman's transfer orbit, which consumes the minimal fuel, or the impulse for which is the minimum. And we say that the optimal orbit. Now, what is the property of this optimal orbit? Notice the way how I have drawn, and that is also what we will see in our calculation. The optimal orbit is such that it is at the point of closest approach to the sun from the takeoff, or it is at the perihelion of the earth, and it is at the aphelion of the Mars, right? So it is at the point of farthest approach for the Mars, right? So it turns out that the optimal orbit is going of the satellite moving. Of course, the satellite is moving in an ellipse. Moving in an ellipse has the perihelion at liftoff L, and aphelion at meeting point R. Okay. So then let us look at the proof here. We are going to find this optimal orbit. The proof involves the finding of this orbit. So suppose our A is the semi-major axis of the satellite. Okay. So what I'm trying to say is, A is this quantity is A, and this quantity is B, right? So that is what we have. A is the semi-major axis. Okay. Just a minute. Let me. Well, this is not true. This is not true. What is true here is that this quantity is 2A, where A is the semi-major axis of the satellite. Okay. So A is the semi-major axis of the satellite. Then what we have is that then the perihelion of the Earth let me call this as A, and the aphelion of the Mars, right? Let me call this as B, right? This is going to be A will be equal to A times 1 minus E, and this is going to be A times 1 plus E. Why? Because A is the semi-major axis of the satellite, the motion of the satellite, right? And so now let us consider a two impulse motion for the satellite. So we consider a general two impulse motion of the satellite of the transfer orbit. Well, I need to name these things. So let me call this as the transfer orbit. This is my transfer orbit that I am drawing here. My transfer orbit is ME, right? So the ending point is M and the starting point is E. So my the general two impulse motion of ME, the transfer orbit, is ME is where we have the liftoff velocity VL to be equal to V theta A and V theta of E, that is the liftoff, and VR of E. So that is the liftoff is occurring from Earth. So these are my two components, V theta and VR. And my landing velocity is this was the liftoff, and this my landing VR is V theta M comma V R M, right? So these are my landing liftoff and landing velocities. Now from energy conservation, I see that VR of E plus V theta of E whole square, right? So this is my kinetic energy from during the liftoff minus 2 gamma by A. So that is the potential energy at liftoff. So A being the radius. So let me call this A is this A, and this A is my B, which is the radius of the Mars or the distance from the Sun, right? So so this is this, and so this is also equal to VR M whole square plus V theta M whole square minus 2 gamma by B, right? And now I can, so this is my energy conservation, and my angular momentum conservation. Angular momentum conservation is A times A being the radius or the distance of the Earth from the Sun, assuming circular orbit. A times V theta of E is B times V theta of M, right? So this is my angular momentum conservation, and now I am going to eliminate few quantities using these two conservation principles, right? And once I do that, I see that I get the following. My VR of M whole square, this is equal to 1 minus A square by B square times V theta E whole square plus VR of E whole square minus 2 gamma 1 by A minus 1 by B, right? So I have eliminated V theta. What have I eliminated? I have eliminated V theta of M. So one variable is gone. So this is an equation in 3 variables, right? So so then I can quickly write down the orbital speeds. I think this is, we are running out of time here. in this module. So I will continue. In our next module, I will continue our discussion on the Hoffman's transfer orbit, and I will show you the form of the orbit where the satellite lands is such that it is always going to be the aphelion of the arriving planet, which is in this case Mars, in our discussion. Okay, so thank you so far for listening. I leave this discussion in this module at a very crucial and a very interesting point. So thank you.